Okay, I think it starts. Okay, one small note. Somebody asked in the break, what is this information leak or mode collapse? So I will give a very simple example of a classification problem where we classify similarities again, not pairs of similarities. And there is, if this is the entropy, the entropy being 0 means that basically 0 entropy means that we always predict with 100% probability one of those classes for all images. So independent of the image, the output would look like this, which corresponds basically to 0 entropy. And then maximum entropy corresponds to, what is the maximum entropy? Corresponds to scattering the probability equally, uniformly. So this would be something like this. So we saw that bus normalization can cause this kind of effects, and in general it's a very critical issue that happens with representation learning when you don't have this human annotated label data and you can't do actually supervised learning where you know what is the cat and dog. Alright, so now we will talk about image clustering. So let's start from the definition. Actually, let's take a step back and even consider why we have a bunch of models. So different methods, we will see different pre-training methods, pretext tasks, objectives. And we ask ourselves the question, how can we evaluate all these learned encoders and learned features? What do they actually learn from these different pre-training models like SimCLR, MoCO, and many other things that we will see throughout the course? So we saw already two types of downstream tasks. Basically, classification was like the downstream task, and we saw like two evaluations. So one was the linear probing, and the other, I don't remember if we see it like this. You don't need to train a linear layer. You just, for its feature, you just take basically a K and N classifier using the features. So for one test features, you decide about its label based on the 20 closest neighbors. So you take majority voting, you see what are my 20 nearest neighbors have, what's the major label, and this is the label. And recently this is a more established evaluation technique for image classification rather than linear probing, because it seems to indicate better the downstream data set in many other tasks like semantic segmentation, object detection, and so on. And the other way, which doesn't include labels, so you still need the labels if you do linear probing in the end, is image clustering. So image clustering is a task where we know in advance how many labels we have on the data set, so a set of images. We know in advance that we have 10 different classes, but we don't know which images correspond to this class. So it's an unsupervised problem. And we will use this to evaluate different pretext tasks. And in general, to give you some indication of the things you can do in practice, in real life, real world scenarios, of how useful is to learn some representations, especially some such low dimensional representations. So for an image of 224 by 224, you have this model, whatever, encoder, and then you take some features F that are just 128 dimensions. So it's a much more compact form of the data, of the initial data. So here the dimensionality is 224 by 224. So you can imagine that the scale is completely different. Instead of working on the image space, we switch our analysis to the feature space of the learned representations. So do we all agree that these representations are much smaller in size? All right? So image clustering is a very challenging task. Even if we know in advance or a priori the number of classes that we know, for example, that image that consists of 1,000 classes, but we don't actually know, it's still unlabeled. So the illustration that I show about mode collapse to either distribute the probability uniformly over these classes or predict one class with 100% probability for all the images in the dataset is a very typical problem in image clustering. What else do we want to know about? Okay, it's a challenging task, and the property is that you have this very hard balance to achieve in general. What is, if we ignore the images, what is the most standard machine learning algorithm that handles data clustering? Have you done that? Yeah, somebody said. Okay, K-means. So why not just use K-means here? Do you think it would, you have something? So basically, it performs equally to random. So K-means is an algorithm that cannot work on images. However, you can apply, you can use all the features of all your images in the training, unlabeled training datasets, and you can apply K-means. This is the points that we discussed before. So what is the simple baseline for deep image clustering? So deep in front of image clustering, it means that there is some deep learning model that produces some sort of features, and then you play on those features. Before 2018, people used autoencoders and use this intermediate or bottleneck representation to use this for image clustering. And there are other methods that are really specific to image clustering that try to train a model from scratch. So deep learning model trained from scratch to learn to do image clustering. But in fact, at least in principle, image clustering consists of two parts, which is different from all the other data clustering methods that we can apply K-means. So first, we need to learn the features. And then we want to predict, basically not predict at the beginning, let's say learn. Since we have the correct features, for example, the foreground for these standard vision benchmarks, the foreground would be like the object, usually in the center. So after we extract the important features, we want to learn the assignment of those features to this priori set of K clusters or classes. And this is achieved with representation learning, with deep representation learning like SimCLR. And since we decouple image clustering with these two steps, even though we cannot use k-means here, we can indeed apply k-means in the on the learn features, so to learn the cluster assignments. So this paper will cover, it's called, the abbreviation is called SCAN. So they take the training data, they do contrastive learning, then they take the features, the learned features, the representations, and they do k-means. And we also have some similar results in the lab, that if you take the best publicly available pre-trained models, you can have, you can outperform all the other methods that used to do clustering in one step. So far, we know that this is the best way to do image clustering, even if k-means, as you see in the right part, does not assign, basically it creates imbalanced clusters. So the imbalanced clusters are not a problem by themselves, but the problem is that during image clustering we have no idea about the data distribution, so we kind of relax the problem and decide that all the data sets are basically all the k classes are uniformly distributed. So an ideal clustering algorithm would assign the same number of samples to each class. And this does not happen with k-means, but it's still important to identify that we can outperform all the literature that try to do this in one step. This is what we call end-to-end clustering methods. Even though we still use deep learning, if you do these two steps together, it's really hard. And cluster degeneracy is the same thing we discussed about MoCO lab. So you either, for 10 classes, you either have like, you predict a probability of 1 out of 10 for each of the possible clusters, or you, for all images independent of the image, you assign a probability of 1 for all the images. So k-means is good, but can we do better? This is the question. And there is this paper from a lab in the Netherlands. This Van Gool is a very famous guy in the deep learning world. So they proposed a strategy that helps us learn the cluster assignments. So of course, here we do representation learning with SimCLR, or as we'll see, more advanced, sophisticated approaches that perform better. Then we compute in the feature space the nearest neighbors for each image, because we saw in the first part of the lecture that there is this alignment that was both empirically and theoretically shown, that views of the same image tend to be together on the hypersphere, and to some extent this applies also to images that share the same label. The problem is that these nearest neighbors, so if we consider them as pairs, they may be noisy. So here you see, for example, the reference image in the first column and its 4 nearest neighbors, but in practice it's not always the case like that. I just want to emphasize that we want to enforce the model to be consistent. So basically, when we can achieve consistency, for example, when we take augmentations of the same image and we push them together, we enforce consistency or invariance to the augmentations of the image. While here, we will try to group together, so make consistent predictions for two images that are neighbors in the feature space, and it's really likely, even though they are noisy, it's really likely that they share the same label. So even though it's not, these pairs are not like perfect pairs, like having the labels and group everything that has the same label, which achieves a perfect clustering accuracy. We group them together, and that's why I needed like another. So basically, they derive an objective to group together the nearest neighbors, and then they do another step to kind of fix the problem that these nearest neighbors are noisy. But we'll not cover this in terms of the next exercise. So their objective is very simple. Here they have the dot product, or the similarity, with L2 normalization. And the problem is that if you ignore this part, that this term will always collapse, in the sense that we'll assign everything, all the images, to one class. So they counteract this. This is what you will implement in the exercise. You will not do the self-labeling step, so we'll not cover that. So the second term is a very is a trick that's called basically entropy regularization. So they have another loss function here with a hyperparameter, and this is nothing rather than cross entropy between basically the average of the images of the buds. So basically they counteract this by pushing the network to distribute their predictions uniformly. And that's why this lambda is the parameter that controls this balance that is very hard to achieve. So you can imagine that it's very hard to find a good value for this parameter lambda. So the bottom line is that we have two loss terms. The second one tries to avoid collapse by spreading the predictions among the clusters, and the first one pushes nearest neighbors together. So this is the reference image. These are the nearest neighbors, and this is the average of the buds of the reference image. So here's the denotation, but in practice we just take the average over the mini buds. And they show some quite good results. On top of taking nearest neighbors, they also applied augmentations. So mining nearest neighbors is just computing the nearest neighbors, and then they also apply augmentation to those images, and they show significant performance improvement. So this may indicate that the layer that is trained on those representations is also able to model some additional augmentation-based invariances. And this relates to the fact that they use these features. They didn't use the best available models. But it's still a significant improvement. So K-means, even though it's a good baseline, it's suboptimal for images, and even for learned features of images. So we'll ignore the self-labeling step, and I just want to show you the improvement. There's a tremendous improvement over K-means, which is basically a naive approach. And they also make some studies, for example, how the nearest neighbors influence the accuracy. And they saw that it's not really sensitive to the number of neighbors. So basically, if you have good neighbors, if you have a good model that groups together images, it doesn't matter if you take 20, 30, or 50. So basically this range here for different datasets. Another thing about clustering, I was also wondering a couple of months ago, how can we argue about accuracy, since we just predict some clusters, but how do these clusters correspond to the ground truth labels. So basically, let's say we have 10 different clusters. So these are the clusters, and these are the I call them ground truth labels. So for training you don't need any label supervision, but for the evaluation you need some supervised validation or test data, and those data are labeled. So how can we achieve this mapping from 10 different clusters? How can we find the optimal solution from how these 10 clusters map to these ground truth labels? So there is a small trick here. We assume that this number is the same. So if you assume that this number is the correct number, so we know in advance the ground truth cluster, there is it has two names in the literature, either the linear sum assignment problem or the Hungarian matching algorithm. So given the ground truth labels and the cluster, it finds the mathematically optimal one-to-one mapping. This algorithm is not related to deep learning or machine learning. It's just that it's really important to understand that we need this mapping, and deep learning is not the solution to all possible problems. So for example, this algorithm, even though it's quite complicated, I provide some resources. It's good to know that in the end we can have some measure of accuracy. So the accuracy is only possible because we learn this mapping. And you can find more information here. And this is some work in the lab, which is basically some additional answers we did here in the lab. Basically, for representation learning, we have this pretext task, we learn these models, these encoders. So how do they perform on image clustering? Which the initial question is like how much label-related information exists on those models. So we have this fancy plot, and so for the purpose of this analysis, we ignore all the blue points, which are like supervised pre-trained models, and we see all this area here. On the x-axis is the clustering accuracy of k-means on the learned features, and on the y-axis is a method we proposed as an alternative to scan, and the distance from the dashed diagonal shows the improvement over k-means. If you check the paper, we also see that we have some significant improvements over scan as well. And you will also implement parts of those loss functions, of the two loss functions of scan and the one we call teacher assemble mutual information. Basically, it's based on point-wise mutual information. So we changed a couple of different things. So during for the scan algorithm says that if you have the training data like CIFAR, you do self-supervised learning with SimCLR on those data. While we argue that if you use the already existing publicly available pre-trained models, they learn much better features than the ones if you train a model yourself from scratch on those small-scale data sets of 50,000 or 100,000 images. So this is the first difference. and then we focus on deriving a better, let's say, loss function that groups together, instead of the scan loss, which you have this parameter to control the balance so that you don't collapse to assigning all the images to one cluster. And this is the loss you will also implement in the exercise. We will ignore this part. I just want to connect the same trick we talked about with MoCO, the symmetrization of the loss. We also use it here, and many methods adopted this trick. So basically you have embeddings. So here you have the image, and here you have the nearest neighbor, which corresponds to the nearest neighbor in the feature space. Then you have like only one head, just ignore the multiple heads now. We have one head, which is like the student head. X corresponds to the subscript for the student and the teacher. And we apply temperature scale softmax. We use a temperature of 0.1, so we increase a lot, as I showed in this animation, the confidence of the output on the softmax. And then we have this loss function, and you can imagine that the first term is similar, the denominator is similar to the first loss of scan, where you have this probability distribution and you have a dot product. It's exactly the same as they do in the first loss term of scan. The difference is that the denominator, in our case, is an exponential moving average over the teacher predictions. And this term is also prone to collapse, to assign all the probabilities in one class. So we derived another hyperparameter. So we raise this term to the power, that's called beta. And for beta between 0.5 and 1, basically we take more into account this term, because here we raise this dot product of probability distributions, predictions, whatever. We scale it down by raising it to the power. So we kind of upweight the average assignment of class probabilities from all the past iterations using this exponential moving average. All right. I guess it's a lot. Any questions about these two methods? Okay, I will try to wrap it up. And basically, I just want to say that this is the last slide. We are the first one to achieve. So this is the supervised classification accuracy on ImageNet. These blue lines indicate only models that were trained on ImageNet, so without external data. So it's comparable to what we did. So the state of the art is something like 91%, while scan was at 40%. So without having the labels, the gap was from 40% to 90%. And with our method, without using external data, we managed to push the accuracy to achieve, in the end, 61%, which basically bridges the gap between those methods, without labels and without external data. Okay, I understand it's a lot. We will wrap it up for today. Any questions so far, or okay? We finished for today.